Hello, good afternoon, good evening, or good morning, wherever you are. Welcome to the third talk in the webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees, families, and colleagues are safe amid the ongoing pandemic. Today's webinar will be presented by Professor Fateme Rezaei of Missouri Science and Technology. I'm Arvind Rajendran with the University of Alberta and have Nick Wilkins, a graduate student in our group. And the two of us will moderate the question and answers. I would also like to acknowledge the contributions of Dan Sidarius, Secretary and Treasurer of the Society, for making these webinars possible. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. Any mention of commercial products during this webinar is for information only. It does not imply recommendation or endorsement by the individuals or the associated institutions or by the IAS. The full disclaimer statement is shown and will be included in the archived video of the webinar. We ask that you consider joining the IAS as a regular member if you're not already one. Our dues are minimal. They're only $20 a year, but support the publication of a flagship journal, Adsorption. They contribute to travel grants and workshops and seed funding for IAS members and affiliated groups. Members also receive free access to the IAS supported materials, including our journal and the Adsorption database supported by Springer Materials. We are also on social media. Please follow us on both Twitter and on the IAS YouTube channels, where you can also find recordings of these webinar series. So today, I am pleased to introduce the speaker, Professor Fateme Rezaei. She's an assistant professor at the Chemical and Biochemical Engineering at Missouri Science and Technology. She received a PhD in chemical engineering from Monash and also did a postdoc at Georgia Tech. She has over 70 peer-reviewed articles. And what is important is also she was the first recipient of the IAS Award for the Excellence in PhD Dissertation back in 2013. And also in 2018, she won the ACS Energy and Fuels Award for Excellence in Publications. She's an associate editor in many journals, and her research interests are in advancing materials and processes for clean energy and sustainable chemical processes. I will now transfer the screen over to Dr. Rezaei. Okay.
Hello, everyone, and I hope all of you are safe and healthy wherever you are. Thank you, Arvind, for the introduction. Before I get started, I would like to thank the organizers, Doctors Andreas Sidel Morgenstern, Dan Siderius, and Arvind Rajendran for inviting me to be part of this webinar series. So my talk today focuses on structured adsorbents in gas separation from formulation to process performance. The outline of my presentation today is as following. I will start by giving a short overview of the current state-of-the-art gas separation technologies and the necessity to move to less energy-intensive alternatives, as well as manufacturing criteria for structured adsorbents. Then I move on to a more detailed discussion on different approaches that have been taken to shape engineer and adsorbent materials, including surface deposition, direct extrusion, and matrix incorporation. And finally, I will conclude the talk by a brief summary and outlook. The majority of legacy separation and purification systems rely on thermally driven phase changes under cryogenic conditions and therefore are inherently energy inefficient. Specifically, distillation columns, despite being highly optimized over decades, still consume much more energy than necessary on a thermodynamic basis. In addition, their operation relies on hydrocarbon sources and therefore produce a large amount of greenhouse gases. Also, the capital and operational costs associated with this technology are typically high. Therefore, advanced separation units that make use of membranes or adsorption processes can offer a more energy efficient alternative to the existing separation systems, especially on the basis of their low energy input to achieve phase changes. Mainly, they avoid, these systems avoid the need to input thermal energy. On the other hand, unfortunately, there are many issues that must be resolved before new non-thermal separation applications can be developed. In particular, with regards to adsorption, recent advances in materials design and discovery have resulted in development of processing materials for various gas separation processes. However, adsorptive gas separation itself is a problem of scale, and the majority of the technology options being considered so far are still in the lab or bench scale stage of development, and if successfully scaled up, they won't be cost effective at their current level of process development. This is something that we've been working on over the past couple of years, and this is the subject of my talk today. Development of next generation separation technologies requires advancement in both materials and process development. We can think of an interactive framework, the one that I'm showing you here. Let me activate my laser pointer here. We can think of this interactive framework that includes a mutual interaction between the materials and processes development components and a constant feedback from each to another one that helps redesign and remodify the original technology. This requires input from both sections. On the materials side, a lot of work should be done on screening, synthesis, post-processing, properties evaluation, and performance. And on the process side, design and simulation, operation, optimization, and scale-up potential are all needed to derive an initial lab scale idea to a final larger scale implementation stage. Now, with that being said, shape engineering and manufacturing of adsorbent powders into practical contactors is a crucial input to this cycle. And in fact, it's a primary driving force to achieve this goal and to help address the scale-up issues of adsorptive gas separation processes in general. Current adsorbents used in most commercial or industrial applications are in the form of pellets or beads. Although they are cheap and available with high adsorbent loadings per unit volume, there are a couple of disadvantages associated with these traditional configurations that I'm showing you here, which compromise the system performance and make them less attractive for cyclic process operations. Such disadvantages include high mass and heat transfer resistances, especially high pressure drop, fluidization, channeling, and maldistribution in the bed. Now, one way to address these issues is to use structured adsorbents, such as monoliths, such as hollow fibers, such as foams or laminates. But how these contactors will improve the performance? For example, we previously showed that structured adsorbents, especially in the form of monoliths, display better mass transfer characteristics compared to traditional fixed beds, as demonstrated here by displaying sharper concentration front. The reason for that is partly because thermal effects typically associated with packed beds can be mitigated, and partly because the thin porous walls of structured adsorbents allow for rapid mass transfer equilibration, thereby allowing for more rapid cycles, and as a result, the volume of the device could be significantly reduced. The same story holds for heat transfer and thermal management. Also, as this figure shows, a key advantage of structured adsorbents in comparison to traditional packed bed systems is that pressure drop through these beds will be correspondingly lower, especially for higher gas throughputs, which will in turn reduce draft fan costs significantly. And lastly, with these contactors, the chance of occurring fluidization or channeling or maldistribution will be substantially lower than that of traditional packing systems, mainly because of the uniform flow pattern through these beds. All right. Now, let's focus on formulating solid adsorbents. First, several important considerations should be taken into account when it comes to manufacturing of structured adsorbents. In shaping crystalline powders into conventional packing, such as, for example, beads or pellets or granules, or even advanced configurations such as monoliths or hollow fibers, care must be taken to ensure that agglomeration of crystals do not impart any changes to their chemical and structural identity. We define several important manufacturing criteria for structured adsorbents, regardless of the shape. These include, but not limited to, retaining crystallinity, which means no structural collapse or conversion of crystalline regions to amorphous regions should take place during formulation or fabrication of structured adsorbents. The other criterion is retaining porosity, which dictates minimum micropore blockage and uniform mesopore size distribution for our structured adsorbents. Retaining functionality is another important manufacturing criterion, which, as expected, we need to have low diffusional resistance and high accessibility to adsorption sites for our structured adsorbents. And finally, impart mechanical and chemical strength, which means that the structured adsorbents must be resistant to attrition or abrasion, and they should also exhibit long-term stability. All right. Generally speaking, crystalline adsorbents can be shaped into different forms by a variety of fabrication techniques. One thing that you should keep in mind is that the choice of a shaping method depends on the specific application, which imposes the preferred shape of the object. In some applications, granules or pellets are required, whereas for other applications, maybe hollow fibers or thin films or honeycomb monoliths are required. Also, the choice of shaping method depends on the stability and functionality of the adsorbent structure. The active adsorbent, the first formulation technology is surface deposition. The active adsorbent may be deposited on the walls of a substrate, such as monoliths or hollow fibers. This approach has been extensively studied to deposit thin films of zeolites or MOFs on the substrates, with two examples shown here: deposition of 13X zeolite on a corrugated metal foil and MOF 74 on a cordierite substrate. This method allows control over the thickness of the deposited film as well as its crystal size and distribution through optimizing the coating process. Also, the mechanical stability and fast adsorption kinetics are other advantages of this technology. On the other hand, we get relatively low adsorbent weight to volume ratio, which is around maximum would be 60 weight%. The active adsorbent may be deposited on the walls for the first step, but also the active adsorbent in another approach could be directly extruded by through direct extrusion technique, by which the active adsorbent could be shaped to a desired structure, like these two MOF monoliths that I'm showing you here, HCAST1 and MIL101, where the large portion of monolith is made of active material, unlike the previous technique, with the rest making up by binding agents or plasticizers to impart required mechanical integrity. Here, the properties of the formed structures are strongly dependent on the properties of the source adsorbent powder, of course, but also the surface tension and viscosity of the binder that could be used to shape these crystalline powders, and the interactions between them. Also, I should mention that mechanical stability and is not as high as the monoliths or the structured adsorbents made by the first method. And sometimes we get slow adsorption kinetics, especially for the thick wall monolithic structures. Now, the third approach that I'm showing you here is matrix incorporation, by which adsorbent particles are embedded within a mesoporous or sometimes macroporous matrix, which is typically a polymeric material. In the past, various zeolites and aminosilicates have been incorporated into polymeric hollow fibers, with some examples shown here. The mechanical stability is high. We get fast adsorption kinetics, and also this approach allows for tuning materials properties. The good mechanical stability results from elastic behavior of the polymer matrix that imparts some good mechanical strength, as I mentioned. Obviously, considering all the three approaches, there are some trade-offs between the properties, structure, and the adsorptive performance of the structured adsorbents fabricated by these techniques that need to be carefully considered and managed during formulation, and also during the choice of the formulation method. Now let's focus on surface deposition approach. There are several well-established techniques employed to deposit sorbents. These methods include in situ deep coating, that involves placing the substrate in this adsorbent synthesis solution, as well as spin coating. These two techniques are the easiest, the most simplest techniques of deposition procedures, as well as other techniques such as layer by layer or LBL, followed by a secondary growth method, or a combination of seed growth and secondary growth, as well as more novel techniques such as electrochemical deposition. I should also mention that the use of these surface coating methods is quite common in the field of membranes processing, in particular for preparing thin MOF films that I'm showing you here. Several bottom-up and top-down approaches have been attempted to form a pattern on the surface, as well as photolithography, which includes several steps like this one that I'm showing you here. First, you deposit a photo developer solution, which is this green sheet that contains metal and linker reagents. Then the application of UV radiation to initiate the reaction, and then formation of the pattern by the aid of photomask layer, followed by cross-linking of MOF crystals by UV radiation, and finally washing the unreacted part. So these are several common deposition procedures have been attempted by many researchers so far to formulate some structured adsorbents. All right. In one of our previous works, we employed different coating procedures to deposit MOF films onto a cordierite substrate for use in CO2 N2 separation. Although the simplest coating techniques, which were deep coating and spin coating, have been successful in depositing zeolites on the same substrate. They failed to grow MOFs in our study. On the other hand, among various coating methods, layer by layer or LBL combined with the secondary growth step was found to be successful in MOF crystal nucleation and growth. And under optimum conditions, a very uniform and homogeneous MOF layer was formed on the presented cordierite surface as shown by these SEM images. In addition, like their powder analogs, the coated samples exhibited high affinity towards CO2 relative to nitrogen, although the obtained capacities were lower than those of powders, as you can see here. However, by controlling the number of layer by layer steps, as well as dipping time and temperature, the adsorbent loading and film thickness can be controlled and tuned. I should also mention that although this growth approach could be a promising method for growing crystals on various supports, the complexity and lengthy procedure, which is sometimes tedious, may limit its widespread use for making structured adsorbents. Film deposition is an enabling technology for integration of novel functional materials into real world practical applications. In a recent study through a novel approach, an electrochemical film deposition of UIO66 MOF was reported using zirconium foil as the only metal source, as you can see from this schematic image. So here, the film formation mechanisms at the cathode and anode resulted in a significantly different coating adhesion strain, mainly because of the formation of an oxide, zirconium oxide, this green sheet on the anode, which acted or served as a bridging layer at the surface. Now, these SEM images here show pristine zirconium foil and zirconium foil substrate after 30 minutes of MOF anodic deposition in the presence of acetic acid with varied molarities. Excuse me. The MOF deposited channels were then used in a custom-built vapor sampling device for adsorption of toluene as a model VOC compound, which was efficient in trapping and concentrating toluene vapor. Overall, the patented deposition capability of the electrochemical method enables the straightforward integration of the MOF as a sorbent film in a sorbent trap device for online analytical sampling and concentration of dilute VOC volatile organic compounds. As you can see from these toluene adsorption isotope presented here at different temperatures. All right. Now let's move on to the second formulation approach, which is direct extrusion. Basically, extrusion is the benchmark method for fabricating monolithic structures. It's a well-established fabrication method, easy paste making, custom-made dies, bulk production at large volume are other advantages of this conventional extrusion method. However, wall thickness and channel size of the extruded monoliths cannot be frequently changed. And despite these advantages, extruded geometries are costly to tune on account of the high labor or machining costs associated with mold production. Considering additive manufacturing or 3D printing, this technique offers a different adsorption fabrication, which complements these conventional methods for fabricating complex geometries with unique mechanical and structural properties. These techniques, additive manufacturing techniques, allow for precisely fabricating three-dimensional devices with desired configurations and optimized properties as opposed to conventional extrusion processes. Also, and some noticeable advantages of this technique include high productivity and low fabrication costs. And also by employing this 3D printing technique, it's possible to fabricate the structures with various cross sections, channel sizes, and wall thicknesses, which cannot be done by conventional extrusion techniques, mainly because of the digitally tunable feature of this technique. Of this, we believe that the digital tuning is the most important benefit, since it allows the geometry to be tuned for any column without mold production. However, I should also mention the drawbacks of additive manufacturing, which are small batch production and relatively long and multi-step operations. Overall, 3D printing technology renders direct material modification in a realistic and economic prospect if these limitations are addressed and properly managed. Considering ink printing techniques, several methods have been reported for formulating adsorbents into structured adsorbents. These methods include direct printing. Let me activate this video. Okay, let me change here. So, direct printing, in which a pre-synthesized adsorbent is mixed with a suitable binding agent and printed into a desired shape. Then we have secondary seeding growth, in which a metal oxide is first printed into a desired configuration, let's say monolith, and then converted in situ to the adsorbent. This method is particularly applicable to MOFs and has been attempted for formulating MOFs into fibers or monoliths. We do have polymer phase separation, which is based on a phase inversion technique commonly used for forming polymeric hollow fibers through a spinning process, by which a liquid paste containing solid sorbent particles, solvent, and a polymer dope transforms into a phase-separated solid structure with nanoscale hierarchical pores. Sol-gel approach is another promising 3D printing method to shape adsorbents into robust structures with high adsorbent loading. It's also possible to shape engineer adsorbents into binderless structures using 3D printing approach, in a similar way as commercially available binderless sorbent beads or pellets. Now, here I'm going to review these techniques in more detail shortly, but before that, I'd like to provide you with a comprehensive overview of the corresponding features associated with each method and how they compare across these methods. Universality is very common for direct printing and sol-gel printing. Considering self-standing rheology, all printing methods fulfill this requirement except polymer phase separation. We have non-flowing behavior. The same polymer phase separation cannot meet this requirement. Considering processing time, we see that binderless printing and sol-gel printing require less amount of time to develop structured adsorbents, whereas for the other techniques, at least 1 week is required to formulate powders into structured adsorbents. Polymer phase separation is great for delivering robust structures with ultra-high mechanical strength. In terms of the retention of solvents, it varies among these different techniques, but most importantly, if you consider number of steps, you see that sol-gel printing and binderless printing are advantages over the other techniques. And in terms of adsorbent loading, most of these techniques, except polymer phase separation, deliver structures with high loading, greatly, in most cases, greater than 80%. All right, now with that, let's just start discussing these techniques one by one. The simple schematic, okay, let me change to laser pointer here. This simple schematic describes the direct printing approach, and these SCM images below show the morphology of a MOF monolith made by this method. Here, the adsorbent is first synthesized and activated, then mixed with an appropriate binder and solvent or any other required additive such as plasticizers to form a paste with optimized viscoelastic properties suitable for printing. Then the structure can be digitally designed using AutoCAD software and printed. In the final step, we have solvent removal and activation, which will be conducted after 3D printing. This approach could yield relatively high adsorbent loadings, typically greater than 85%, with high porosity comparable to that of parent powder. However, lowering the amount of binder will compromise the mechanical stability of the final pieces. We have successfully employed this method for various sorbents such as zeolites, mixed metal oxides, MOFs, ZIFs, and also aminosilicates. Some of the adsorption performance results of self-standing MOF 74 monoliths are presented here. As you can see, the adsorption capacity for MOF monoliths prepared by direct printing is comparable to that of parent material. I should also mention that some of the disadvantages of this technique include long preparation time as well as some degree of crystal decomposition during formulation process. This is something that we observed while formulating some MOF materials. There's also a slight chance of penetration of binder and printing solvents into the pores, which basically decompose, which reduces the accessibility to active sites in the adsorbent pores. Other research groups have also employed this technique to develop 3D printed ZIF 8 adsorbent monoliths with different scaffold designs, as you can see from here. For example, in a recent study, the open scaffold design strategy with narrow channeling was shown to enhance biobutanol vapor transport. However, small side channels of around 250 microns led to maldistribution of the flow at the inlet. The adsorption results for biobutanol recovery obtained for different adsorption-desorption cycles demonstrated fast cycle time for this monolith and also sustainable capacity, with the capacity being fully restored upon thermal regeneration of the monoliths. In addition, the authors, the investigators performed mixture breakthrough experiments, and the results demonstrated that a high amount of butanol could be absorbed in dynamic conditions close to the pure component capacity. Direct printing allows for varying the cell density of the monoliths and consequently fine-tuning their adsorptive performance. To achieve this, we previously synthesized zeolite 13X monoliths with 200, 400, and 600 CPSI or cell per square inch and investigated their dynamic adsorption behavior in CO2 capture process. From CFT simulations, interlocking channels improve fluid contact, and also we expect to see the increase in cell density leading to more contact and contact time and enhancing in film transfer. However, we have found the opposite to be true for our monolithic structures. So here, as expected, increasing the cell density gave rise to enhanced film mass transfer coefficient, mainly increasing the cell density from 200 to 400, nearly doubled film mass transfer at every velocity investigated here, 60 to 200 mil per minute. Similarly, by increasing the cell density from 400 to 600 CPSI, we observed around 30% enhancement in film mass transfer coefficient. However, and as apparent from the breakthrough profiles, here the enhancement in film mass transfer didn't improve adsorption kinetics. Instead, we observed that breakthrough fronts broadened at both higher cell density and inlet velocity because they were limited by poor mass transfer. Specifically, increasing the fit velocity and the cell density reduced the CO2 residence time because of the gas throttling effect. These are the results of monoliths printed through direct printing with varied cell density. By performing some modeling investigations, we quantified the mass transfer parameters as presented here in this table numerically and the fitted breakthrough profiles here. The takeaway message that I'm going to deliver here was that although the higher cell density does enhance film mass transfer, the limitation posed by the KP or poor mass transfer coefficients several orders of magnitude larger, and for this reason it does not lead to enhanced mass transfer. However, if the issue of KP, film mass transfer, were addressed, then the mass transfer rate, overall mass transfer rate, would be more dependent on the cell density for our structured adsorbents. In conjunction with the previous slide I discussed a few seconds ago, this slide shows how porosity can be tuned through printing as well. In other words, we're also able to vary porosity for 3D printed structures using or by direct printing approach. This could be achieved by varying the printing paste composition, either by removing or doubling the organic additive, or by adding a microporous binder such as kaolin. Previously, in making these monoliths, we used a mesoporous binder, bentonite clay, and then in order to vary porosity, we decided to add a microporous binder such as kaolin to see how porosity could be tuned. And these SCM images visually depict the changes in the porosity of the monoliths and creation of meso and macro porosity upon variation of the composition. One thing that we found was that by doing this, the mesoporosity can be enhanced without weakening the mechanical stability, which was a great finding for our application. Now, how about the porosity effects on dynamic adsorption behavior? Simulating the concentration wavefronts and estimation of mass transfer parameters indicated that increasing mesoporosity reduces diffusional resistance and enhances mass transfer. To put it numerically, the Kp values, the Kf values, and overall K values were estimated, and it was found that Kp, especially poor mass transfer coefficient, could be increased substantially in the meso or macroporous monoliths relative to the original 600 CPSI monolith formulated by a mesoporous binder. All right, now moving on to the secondary seeding approach. The method, again, is schematically shown here for MOFs. So from this procedure, a mixture of binder and metal salt is first mixed in a solvent, and then by adjusting the paste viscosity, it could be printed into a desired structure, followed by organic plasticizer removal to yield the second seeded monolith. In the next step, this seeded monolith was used to facilitate the MOF growth used by a salvo-thermal synthesis approach, which gave rise to a self-standing MOF monoliths. The metal weight loading in the binder support could be varied systematically to optimize the MOF growth while retaining the mechanical integrity of the final structure. This is the most or noticeable advantage of secondary seeding growth. So here, the obtained UTSA monolith with the 90% loading exhibited similar textural features while improving upon mechanical strength. Using this technique, we managed to obtain MOF loading of around 90 weight%. We utilized these monoliths in separation of various binary gas mixtures and obtained similar adsorption characteristics to their powder analog. In comparison to directly printed UTSA 16 monolith, UTSA 16 monolith prepared by this secondary seeding growth not only showed higher MOF loading, but also higher compression stress indicative of its robust structure. This is what we actually found. And also the adsorption isotherms, as you can clearly see from here, were quite, CO2 adsorption isotherms are quite comparable, proportional, of course, to the MOF loading of the monoliths, very close to that of adsorption isotherms for powder MOFs. And I should also mention that the adsorption overall, the adsorption characteristics were unaffected, remained intact using this secondary seeding growth. All right, let's move on to the next technique, polymer phase separation. Usually organic, inorganic materials. We all know that these composite materials have emerged as promising candidates for use in many wide range of gas separation processes, mainly on the basis of beneficial synergistic effect of both constituents. This is the basis for incorporating inorganic adsorbent particles within an organic matrix such as polymers through 3D printing. To develop adsorbent structures through suspension in a polymer dope, first these adsorbent particles are first dissolved in a polymer, right here, and then rolled under a heat lamp until a homogeneous dope could be obtained. Then the polymer adsorbent is precipitated out by dropping on a non-solvent through 3D printing method, and then the follow-up activation and the solvent removal. This method has been successful for zeolites 5A and zeolite 13X, as well as some MOFs, such as HCOST1. However, for some other MOFs, such as MOF 74, the dope formation decomposed the MOF particles. And this method failed to make any MOF monolith using secondary phase, polymer phase separation. Nevertheless, we use these decomposed particles as growth seeds to generate a film on the surface. So these are seed growths for the decomposed MOF 74. So we use them as seed, basically seed growth particles to generate a film on the surface in a secondary salvo-thermal synthesis step, as you can see here. And this small SEM image clearly shows the formation of crystalline phases of MOF 74. Overall, this is a promising method, and the formation of a liquid dope enhances particle dispersion and produces better rheology for the printing paste. However, as I mentioned earlier, the loading, the loading obtained by this method is limited, mainly because increasing the loading results in the difficulty of the printing, and also further mechanical instability of final substrates. All right. A key factor in successfully printing a viscous liquid is to control the flow of the paste during extrusion, which is achieved by controlling its viscosity. Rheological properties of polymer sorbent paste dictate sorbent loading. The viscosity of the paste should be sufficiently high to avoid the collapse of the structure. This is what we expect, and also to mitigate spreading effect of liquid paste with well-controlled deposition during and after extrusion. Looking at the viscosity shear rate profiles here, I'm showing you of the two polymer sorbent paste prepared for extrusion. We noted that higher shear rates displayed good flowing characteristics, which means low viscosity, whereas a high viscosity is obtained at low shear rates. So these results are generally indicative of a good extrusion behavior. In other words, low viscosities at high shear rates for both polymer sorbent paste investigated in our preliminary investigations. Another noticeable finding was much higher compressive strength for polymer sorbent monoliths than that of self-standing monoliths prepared by direct printing. Other advantages of this technique include improvement from direct printing, easier to print, and more stable and polymer less the polymer phase minimally affecting pore accessibility. The printing strategy reported here can be easily expanded to other organic, inorganic composite materials with different polymers and inorganic particles. Despite this, an associated drawback that may limit the applicability of this technique relative to other materials is low adsorbent loading, as stated before, up to 60 weight% compared to those obtained from other methods. And also, increasing the loading will adversely affect the rheological properties of the paste and render it unprintable. This is something that we actually found. In terms of adsorptive performance, we observed a slight reduction in working capacity from loading, which was likely caused by low activation temperature. All right. Another novel approach that we have been working recently is binderless printing. This technique will definitely expand the universality of additive manufacturing. We have recently demonstrated its feasibility for shape engineering of several zeolites into binderless monoliths. And this technique was inspired by the current manufacturing processes for binderless beads and pellets. This is advantages why, since unlike other previously discussed methods, this technique doesn't require any adhesion to an inner binder, which oftentimes leads to reduced weight loadings as well as deactivated pores. The first step in 3D printing binderless zeolite and scaffolds lies within a selection of suitable binding agents. Why is important? Because producing 100% pure monoliths necessitates that the binder both be completely organic, so that it can be removed during calcination, as well as capable of achieving a favorable rheology. Rheology is very important, otherwise the paste cannot be printed. What we found was that biopolymers such as gelatin are suitable candidates for this purpose. Another advantage of this method is rapid preparation and the simplicity. It requires only 2 steps to prepare structured adsorbents. All right, the XRD patterns here that you see confirm consistent crystallinity with the parent zeolites. To demonstrate this proof of concept investigation, we utilized these binderless zeolite monoliths in CO2 capture and observed faster uptake than commercially available beads or monoliths. Also, I should mention that, as you can see from here, the structured adsorbent exhibited slightly higher equilibrium capacity than the powders, which is currently under investigation as to how or why this is happening. But we repeated these synthesis procedures and made different batches, and every batch gave the same behavior. I should also mention here that despite high adsorption loading, as you can expect, nearly around 100%, the mechanical integrity of these structures is of high concern. Well, we can address this drawback by adding small amounts of a binding agent with compositions less than 5% to achieve the desired mechanical integrity for the final structures. Moving on to sol gel printing approach. On the basis of previously reported sol gel approaches for producing hierarchical MOF scaffolds, we initially hypothesized that MOF monoliths could be produced by gelating their procedures, followed by printing and then heating the as synthesized scaffold to coordinate the linker metal complex. In this method, irregular nanoparticle packing during gelation and printing steps leads to highly loaded MOF monoliths with hierarchical pore systems featuring both intraparticle micropores and also interparticle mesopores. This technique has produced interconnected MOF particles whose topologies were consistent with H-cast1 in the literature, as you see here, with 80% weight loading. The other 20% came from the bentonite or PVA, mainly PVA. And also we investigated the CO2 adsorption performance of these novel sol gel printed scaffolds, and we showed low adsorption, unfortunately, equilibrium adsorption capacity, which was around 60% of the powder's capacity. And we believe that this low capacity was obtained because we didn't get 100% conversion of precursors to the final MOF. The fractional uptake measurements and the corresponding diffusivity values estimated from these profiles indicated that desolvation, which is or solvent removal, produces large mesopores that promotes effective diffusivity to the hierarchical pore network. In addition, the gelated monolith gave better mass transfer than the directly printed monolith for the same MOF because it had an open mesopore structure, which enhanced the rate of mass transfer. All right, so now with that, we're done with the 3D printing techniques. Now moving on to the third method of structured adsorbents. I noticed that we don't have that much time. I'm going to make it quick. So matrix incorporation involves incorporating solid particles into a matrix. This method has been widely investigated using a spinning technique, which often results in a uniform zeolite dispersion, as you can see from these nice images, SEM images, throughout the matrix. Examples, several examples are zeolites incorporated into a polymeric hollow fiber, main cellulose acetate polymeric hollow fiber, and their performance in CO2 capture. The hollow fibers' open geometry and high surface area to volume ratio usually allow the CO2 to rapidly saturate within the fiber and therefore giving rise to a steeper front, indicating the incorporating zeolites within polymer hollow fibers can be used to manufacture relatively high capacity adsorbents. Another similar examples that is presented here is the mesoporous silica particles incorporated into a polymeric hollow fiber as the other technique, followed by a post-infusion step by which amine moieties were loaded into the mesopores of silica particles. And then the rapid temperature swing adsorption process evaluation showed that fast cycle times could be achieved with high adsorption capacity and rapid kinetics. And more importantly, in full rapid temperature swing adsorption cycles, high purity CO2 was achieved, and the adsorption enthalpy recovery was also high. So this technique was also demonstrated through 3D printing as well. Some of the results are presented that I'm going to skip considering the time limitation that we have. But I would like to briefly discuss MOF growth on carbon hollow fibers. This is something that we also performed previously. These carbon hollow fibers required acid functionalization for growth, and therefore the fibers must be first activated with a mixture of concentrated acids to attach hydroxyl groups on the surface before MOF growth. Then the mechanism of MOF growth is based on chemic chemistry that actually is shown here, where actually the metal center attaches to the OH groups, followed by ligand attachment, followed by metal attachment, and so on and so forth during solvothermal synthesis to grow the MOF film. I should also mention here that these carbon hollow fibers were obtained by pyrolyzing polymeric Torlon hollow fibers. Specifically looking at MOF 74 topologies, we notice a flower-like structure here. And as opposed to what has been reported in the literature, we believe that this might have been caused by the OH groups deprotonating the ligand and forming structure which is not interconnected. This approach gave rise to relatively low MOF loading, around 40%. Okay, and lastly, I would like to emphasize that evaluating the equilibrium and dynamic performance of structured adsorbents is definitely necessary, but not sufficient. Their process performance in terms of productivity, purity, and recovery, throughput, and energy consumption all must be thoroughly investigated in a real setting. We are currently investigating these performance metrics for our structured adsorbents, but there are some examples in the literature that focus on such studies. For example, most recently, the performance of a zeolite Y-zeolite monolith with square channels was numerically investigated in an intensified 8-bed 14-step vacuum pressure swing adsorption unit to capture CO2 from a high pressure stream in a small scale steam methane reforming process. As you can see here, the main findings of this study was that were that the productivity of the monolithic VPSA process in terms of its CO2 production capacity was almost double than the values reported in the literature for benchmark amine scrubbing capture plants for larger scale steam methane reforming applications. It was also reported that the cycle time is much more shorter than that for pelleted adsorbent systems under the same conditions with an equally sized fixed bed. The pelleted adsorbent system was also found to have a lower working capacity between the same blow-down and evacuation pressure than the monolithic adsorbent systems. All right, with that, I'd like to sum up this talk by summarizing some of the key points here. Moving from conventional gas separation technologies to more energy efficient processes requires advancement in both adsorbents and processes The novel structures can fulfill many of the requirements of advanced gas separation processes. We also believe that the 3D printing technique offers an alternative, cost-effective, and facile approach to fabricate structured adsorbents with tunable structural, chemical, and mechanical properties for using gas separation processes, and also shaping solid adsorbents into practical contactors is solely application driven. Considering outlook, two important notes to mention here. For formulation techniques should consider not only materials' structural and physiochemical properties, but also their actual process performance under realistic cyclic conditions. And finally, for any adsorptive separation process, it's imperative to assess the performance of structured adsorbents with respect to working capacity, pressure drop, mass transfer, as well as heat management. And with that, I would like to acknowledge the past and current members of our adsorption and separation lab here at Missouri Scientific, especially students who contributed to past and ongoing 3D printing projects, Shane Lawson and Harshul Thakur, as well as funding sources that supported our work. Thank you for your attention, and I'd be happy to answer any questions you might have.
Thank you, Fateme. Are you able to hear me?
Yes.
Okay, wonderful. Yeah, thank you so much for this nice overview of structured adsorbents. I'd ask folks who are here on Zoom to post your questions in the Q&A panel, as you can see here. And I also have some questions from YouTube already, so I'm going to transmit that as well. So one question comes from Arshdeep Singh. So the question is, what are the typical binding and support materials used for making monoliths? And does the kind of binder or support have an effect on adsorption capacity?
There are different binding agents that could be used to formulate solid adsorbents, typically polymeric binders and amorphous silicate-based binders, such as bentonite clay, such as kaolin, and considering polymeric binders, PVA is usually a good case. But this is a very general question. The answer is really dependent on the type of the adsorbent material that you have. Initially, we did a lot of trial and error experiments to determine the right binder material for our case. But if you consider 3D printing, the most important effect of binder is the rheology of paste. Some binders do not give rise to a good viscosity that could be printable. And also, as I mentioned earlier in one of the topics, the type of mesoporosity and microporosity of the binder matters, because the attachment, the attachment and surface tension between the binding agent, binding molecules, and also the binding particles and the adsorbent particles play an important role in determining the final properties and also structural integrity of the pieces. So yes, the answer is yes, and it's very important to find the right binder for the adsorbent, any given adsorbent.
Excellent, thank you. So the next question is from Luis Aguirre. Can these monoliths be used also at high pressures?
Absolutely. So one of the main applications of making these structured adsorbents is used in pressure swing adsorption processes, right? That have high pressure requirements. In order to utilize these structured adsorbents under high pressures, mechanical stability is the key, in addition to other performance metrics that I mentioned earlier. So before doing that, we need to make sure that attrition doesn't doesn't happen in the earliest stages of formulation. For that, we need to make sure that mechanical testing is frequently done over the on the structured adsorbents. And also, currently the size of these structures, these shaped adsorbents, is important when it comes to the actual application. If you want to utilize them in a large bed, you need to make sure you print them or you formulate them in a size that is suitable for your bed. So this is also some by increasing the capacity of the printer, or perhaps by doing other alterations to the procedure to develop large size pieces. So the answer is definitely yes, especially for zeolite materials. That's something that we have done and we're currently working on. But speaking of MOF materials, this is something that we need to investigate more. And the most important factor is, I would say, mechanical integrity, that you need to make sure that particle loss doesn't occur under high pressure conditions.
Thank you. I have about 3 more questions. The next one comes from Marco today. Have these materials been tested over several cycles? And if there are changes in performance, are they mainly due to the monolith structure or the solvent structure?
So that's in fact a good question, and it goes back to my note about investigating the actual performance of these materials under realistic cyclic conditions. Yes, we investigated the performance of several of these monolithic structures over multiple desorption cycles, mainly at low pressures and under different temperatures. We did not really observe any capacity loss or noticeable capacity loss for our adsorbents, especially for most robust adsorbents. But for some other materials, especially aminosilicate adsorbents that we, in the form of 3D printed monolithic structures, will observe some capacity loss due to amine leaching. So this is a very broad, again, question. It really depends on the material that you are investigating. For zeolite materials, for most of MOF materials, the answer is no, but for some amine incorporated materials, yes, we observed some capacity or loss. The good news is that you can reinfuse these amine loaded structures and recover the capacity.
Okay. So the next question is from Igor Nikitin from YouTube. So is there any trend between shear rate and porosity of the monolith?
This is something that it requires a lot of, again, investigation. So if I can
refer to slide 20.
Okay, let me go 20 here again. Okay, slide number 20. Okay. Oh, you said 20, right?
Yeah, 20.
So usually, okay, 20, let's go back here. All right. To have a good, I would say, flowing characteristics, we need to have low viscosity, a low viscous ink or paste. A high viscosity is usually obtained at low shear rates. So this is the relationship that we found for these materials. And low viscosities at shear rates is favorable in order to have a good extrusion behavior for our monoliths.
Okay, excellent. The next question comes from Isabel Esteves. How do you pair the paste viscosity with printing parameters? Do you have any guidelines for that?
What was exactly? I couldn't get the question.
So how do you combine the viscosity of the paste with the parameters that you set in your 3D printing system?
So you can vary the viscosity by manipulating the amount of solvent that you can add to your paste, and also the way that you add. Sometimes you're required to add solvents dropwise. Sometimes you need to add solvent in larger quantity. So this is how you can vary the viscosity of your paste. Sometimes it's required to have a combination of different solvents in order to achieve a rheology or viscoelastic properties that you need to have a printable paste. So the answer is changing the way that you add the solvent, the amount, that the type of the solvent, and the amount of the solvent that you need to prepare these pastes.
So we have the last question. This comes from Shaya. And this is, have there been applications in liquid systems?
For liquid systems, yes, we're currently looking at using some of these monolithic structures for water purification applications. I didn't provide any information on that because that was mainly for gas separation. But yeah, and I'm aware of different research groups that have actually used these structured adsorbents for a variety of liquid phase separation processes.
Excellent. So thank you so much, Fateme.
Thank you, Arvind. I appreciate that.
Yeah, just hold on for a minute. We just have a couple of announcements.
Mm-hmm.
Let me just pull out my...
Should I stop share?
Yeah, I think that should work. So this is just to remind our audience that we have another exciting webinar coming up tomorrow by Professor Randall Snurr, and this is on using molecular simulations to predict adsorption properties. Note that this is at 10 a.m. New York time, so we hope you will join us for this very interesting webinar. What I would also like to point out is following that on the 29th, we have a very nice talk about high pressure adsorption by Dr. Ronnie Pinney from Imperial. And starting May, we have a series of lectures in a variety of topics, such as characterization through diffusion measurements, breakthrough experiments. We have a nice talk on carbons and how to bridge materials and processes, and a whole bunch of talks on MOFs, and more MOFs. So thank you so much for attending. Do give your feedback and follow us on our social media channels, and wherever you are, be safe and stay healthy. Thank you so much.
Thank you, everyone.